Good morning. Welcome to Krishna's class. We continue with our exploration of Lebesgue integral of measurable functions. Last time, if you recall, I concluded my lecture with a theorem on the continuity of integration. While stating this theorem, I missed a very important condition to be mentioned in the statement. This was the integrability of f. However, if I recall correctly, while proving the theorem, I felt the need for it and then wrote it down there. But then I was not in a position to incorporate in the statement of the theorem. So we will just briefly recall this, and then you can correct the previous version accordingly. So this was the theorem. The continuity of now the statement, this is the line which I missed. So let f be integrable over a measurable set. Yes. This is the assumption which I have missed to state last time. Of course, I used it later. Let En be a ascending collection of measurable subsets of V. Then what you have is this integral over union 1 to infinity of f that is one statement. The second statement under the same circumstances is this: if En be a descending countable collection of measurable subsets, then integral one to is equal to limit n tending to infinity Now this is both coming out of an application of the uh, bounded convergence theorem. Okay, in both the cases what one does is the following. You just take, see, the first case En is a ascending collection of measurable subsets. Then you see that this is equal to you have the sequence En, so you have this En plus 1 contains, this is the condition of ascending sequence. Then of course we talk about the restrict f to define Fn equal to chi of E. Now you see that since En are measurable subsets, f chi En is a measurable function. Okay. Now you also see that Fn is bounded above C, less than or equal to. So you what you get is a sequence Fn. This is true. And you also have this condition that integral f. So these are the conditions that. So you see, this is the right recipe for applying the what is called the bounded convergence theorem. Okay, and it follows from the theorem. The conclusion of this theorem follows, right? Because this is what you have, integral over 1 to n. n 1 to n. This is what you get. So integral this is equal to what you have. You have union 1 to infinity ek, k equal to 1 to n. Okay. So this is the limit of that, because it's an ascending sequence. And you see that if this is this, in that case becomes limit M K F, and that's equal to, oh no, sorry. I think this who follows the following thing. So you have of K of Fn. Okay, and what is Fn? Fn is equal to, this is equal to limit n tending to infinity of, you have this one, so it is actually chi En. So this is going to be integral over En cos, or rather I would write it this way. A similar proof works for the second part also. But in both these situations, you have to apply what is called the bounded convergence theorem, because you have a sequence of functions Fn constructed which is finite, which is supported by En. Fn is supported by En, and now these functions are all bounded by F. Okay, and then you have Fn converges to okay. So what you do is you work on this one integral. See, you have this one. This is equal to limit n tending to integral over En or Ek of Fn, and that of course you can replace by this, and which turns out to be 0. That's the result. That's how you prove. The proof is worked out in the. So this is true for both the cases. So I just stop here with that. The important point is that the one that I have missed, namely that assuming f to be integrable over. Okay. Now we take up the concept of uniform integrable. See, before we state the theorem, what is that you expect from this? So we work with Riemann integral. Riemann integrable functions. And the Riemann integral. What does it mean? It means that we will be working with functions f that is bounded and on a bounded interval and defined on a bounded interval. And bounded. So f is a bounded function which is defined on a bounded. Okay. For such functions, now we are talking about Riemann integrable functions. Okay. So we assume that the Riemann integral exists. Okay. First of all, while defining Riemann integral, our strategy is to divide the domain into subintervals. Okay. Now this is the thing that you have. This is an interval AB, bounded interval, and I mean I am drawing a non-negative function, but you can work with a general function. This is a bounded function. Now what do you expect? You see that if you take an interval xi minus 1 to xi and take the integral of the function over the interval xi minus 1 to xi, that is computing this area. So you are taking this one, the Riemann integral of from xi minus 1 to xi of f. Now this is of course bounded by what you have m, which is the bound for f, and xi minus, we are assuming xi minus 1. This estimate is there. What does it mean? It means this integral can be made as small as you please by choosing the interval length xi minus 1 small. Okay. So this is one fact that we observe. What is the analog of this for integrable functions over E? So analogously, so what do you have? So one can write this way: given epsilon positive, there exists a delta positive such that Riemann integral of over xi minus 1 to xi if I n is an interval of length less than delta, then the Riemann integral of is less than epsilon. Now this is the crucial. Given epsilon positive, there exists a delta positive such that if I is an interval of length less than delta, then now you see, for Riemann integral it is quite obvious thing, because you are taking a function that is bounded, because what you get is this: for any interval, see, this is going to be this part, the Riemann integral of this is going to be less than or equal to m times this, which is less than or equal to m times delta. So given epsilon, all that you need is choose epsilon equal to delta divided by, where m is the bound for f. Then you get Riemann integral of xi f is less than. This is the estimate that you get. So what does it say? It says that if f is a Riemann integrable function, then you have for every given an epsilon positive, you can find a delta such that if you take any interval, subinterval of the domain, which is of length less than delta, then the Riemann integral of f on that interval is bounded by epsilon. So this is the result that you get. And yeah, this is something that we have for this one. And in Riemann integrals, of course, you work only with intervals and lot of other things. Now we make some observation. What is this xi minus xi minus 1? Xi minus xi minus 1 is the length of the interval, or what you call in our language, it is the Lebesgue measure of the interval. Okay. So the length is the Lebesgue measure. So the length is, so you see that length of is the this interval. Okay. Now you see, you are assuming here f to be, we are working only on bounded functions. Not necessarily continuous. That is not the part of the assumption. Now you see, the question that you ask is the following. Okay. See, instead of this interval, AB, you identify with a measurable set. Okay. Secondly, we have assumed that f is bounded here. Therefore, you see that integral mod f a to b is finite. Now this is to be replaced by the Lebesgue integral over E . The significant point I want to make is that E need not be a bounded subinterval of R. However, we need some condition on that. What is that condition? Okay, we want some restriction on that, and that restriction is automatically the following. That is further assumed. Measure of E is fine. Some place you would need this requirement. Okay. So these kind of results will have to be taken care of. So what will be the analog of this result? Let us craft this result. Given, so we take a function f which is measurable on E, okay, and we assume that integral over E of f is finite. This assumption, okay, that is automatically there in this. Now the role of E is taken up by the interval AB in the case of a Riemann. Okay, so what is going to be the result that you are getting? Let me try to state this. Given epsilon positive, there exists a delta positive such that, you see, mod xi to xi minus 1, or you are talking about a subinterval here whose length is less than, such that if A is a measurable subset of B with measure of A is less than delta, then we have integral over A f. Or I say integral over f less than. So compare these two statements. What do you get? See, you are taking a Riemann integrable function which pre-assumes a few things, namely that f is bounded on a bounded interval AB. So your E that you are getting here in this statement is the interval AB. Then, of course, we have this, we are taking f to be an integrable function. That means this condition is satisfied over E, which is corresponding to what you call integral A to B mod f is less than infinity, which is already there for it. Okay. The third condition. So, what is the statement that we have? Now come back here. So the statement that we have is something like this. I have also given the path through which you have to prove it. It says, given epsilon positive, there exists a delta positive such that if I is an interval of length less than delta, here I have correspondingly, if A is a measurable subset of E with measure of A less than delta, then integral of, here Riemann integral of this is finite, and this is less than epsilon, and here the integral of mod f is less than epsilon. So this is the result. So let us now, so this is one part of the theorem. Second part of the theorem is something that we, or a converse of this result, we try to build. There, if this is possible, if this condition holds, that is given epsilon there exists a delta such that measure of A is less than, whenever A is a measurable subset of E, if the measure of A is less than delta, then integral over A mod F is less than epsilon. That is the condition that we need. This would imply, this is something which we don't assume, imply integral over E mod F. Under the assumption that we also assume measure of E is finite. Okay, right? So this, under this assumption, the converse would. Okay, so let us state the theorem, but all this require a lemma to this result. Okay, so we start with a statement of the lemma. So Riemann integrable functions are Lebesgue integrable. Therefore, all those results that we state for Lebesgue integrable functions should hold for Riemann integrable functions also. It is always better to understand the statement of the theorem in the context of Riemann integral. Then that will give a better insight into what we are writing. Otherwise, it will look abstract. So, one of the results that we want to prove is the following. Suppose, see, let us once again go back to the case of Riemann integral. Suppose AB is a bounded interval. Be a bounded interval. Then AB can be written as the disjoint union of a finite collection of subsets of length here I will write intervals. Of length less than for any delta. What does it say? See, you have the interval AB. What is the total length of this interval? D minus. This is finite. Now, suppose you choose a positive number delta positive. Then you can find a number n, a natural number n, such that AB is written as n, where these are all intervals, ij intersection I k is empty whenever j is not equal to AB can be written as the union of finite set of intervals such that the length of ij is less than. So for a given delta positive. This is the result that you can prove. I mean, it's obvious. It's very clear. Okay. You can certainly set up this, and I don't think it needs any further. So what you do is you divide this by b minus a by delta. Okay. And then find a number n such that this is greater than n. So find n So I'll say less than. Okay. So you choose a number n such that b minus a by delta is less than. Then you get, you can work out intervals of this kind, and each interval is of the form xi minus 1 to xi, and whose length is less than delta, and such that these intervals are so designed that they are mutually disjoint. Okay. So this result is something which we shall need. But what is going to be the corresponding version in the present scenario? Obviously, as we did earlier, see, we can have the measure of E finite is one option. But can we go beyond that? So we will set the measure of E. Okay. So we have the interval AB, that is the length, or what you call the length of this, is equal to b minus a, which is fine. And the corresponding thing would be, see, we are taking this, instead of AB, we translate it to yes, measurable subset. So you have, this is the measure of this, and what you have is measure of. So that's the corresponding change there. Then what about the i's? The subintervals are to be generalized to measurable subsets. Say A is, let A be and then what more you need, what you are saying is that given positive one can write E to be union J equal to 1 to N AJ, where measure of is finite and AI intersection AJ is whenever I different from, right? So what we are asserting is that under this condition we can write this as a finite union of measurable subsets with measure of AJ finite and such that AI intersection AJ. This is the result that we are going to first see, and that is obvious in the case of intervals, okay, because once you fix your delta and you have measure of AJ is delta, so not in there but delta. Now this is possible for any measurable subset of R. This is what we are. So the lemma, let us take it. Proof runs actually along this direction. It's not different. Let E be a set of with finite measure that takes the part of the interval A. Then E is the disjoint union of a finite collection of measurable subsets just a measure less than delta for any given. So what happens is the number of partitions. So what you are saying is that E is equal to union I equal to 1 to n ai, where measure of ai is less than, and ai intersection so this is the statement that we have written. Given delta positive, you have this property. So let us prove this. Proof is very simple. Now, why this is so? See, first of all, you observe that E need not be a bounded set. Okay, right? For example, you take the entire set of rational numbers. This is not a bounded set, but it is measurable, and its measure is equal to 0. So it has a finite measure. Okay, or you can look at this one. I just make this as a mark. E need not be cannot be a bounded set. That is one. For example, you take E. All that we need is we assume only measure of E is finite. So that is there are subsets of R whose measure is not finite. Okay, but the set itself may not be bounded. For example, you take En to be equal to M2 square. Or even this. So or be on the safe side. What is this? This is actually 1 to 2 union 2 plus 1 by 4. Okay. So 2 plus 1 by 4. This is the set. So you take E to be. What about this? E is not bounded. Whereas, if you look at this, you see that the measure of E is equal to sigma n equal to 1 to 1 by n square. And this, of course, you know is 1. Okay? But this is not a bounded set. Right? So this is something of a very, very nice example where this is not a bounded set, but the total measure of this is still finite. Every subset has a positive measure. But then eventually this is what it is. So this, it is better to remember that in the Riemann integral, that part is simple because we are taking only bounded intervals. Therefore, the length of the interval is certainly finite. Okay. Right. Now, what does this say? Okay, this itself is a expression. This is not an expression of the. This is not an expression of the theorem, because we are only talking about finite union. So it's something non-trivial that we have to work. Okay. What do you observe here? In this example, you see that if delta is positive, then one can find there exists an n such that sigma n plus 1 infinity 1 by n square, because this is a convergent series. So what does this mean? This means the measure of the set. So the measure of, so we take say, let us take En plus 1 equal to this is equal to union k equal to n to infinity k. This part you write as En plus 1. Okay. Now the other ones you write as En. So you have got now E is now E1 plus etc. Where each EI, so for 1 less than or equal to I less than equal to N. I write this way so that I have therefore you have this. See, now look at the length of each of this. This is finite. Okay. This is a bounded interval, this is a bounded interval, these are n bounded intervals. You can subdivide each of them by, further to make it the length less than delta. That is possible. Okay. So, and this is already under control, and we have chosen this. Okay. Submit. Has therefore you can write E as this. E as a union of finite set of measurable subsets whose measure of each of the subset is less than delta. So for any given delta you can do this. Yeah. So let us now work out the proof, the general scenario, because this is the caution that E may not be a bounded set. So how do you push the argument across? Given E, measurable with measure of finite, we define then what you have, sorry, slash this, right? Then what do you have? See, it's just shrinking down. The sets En are shrinking down. Therefore, what you have, since is contained in we have En a descending sequence of measurable subsets okay. Now you see that measure of En is less than measure of for every n, which is finite. This is okay. Therefore, you have, and further you have measure of En plus 1. is less than or equal to measure of En, and each of this is less than is minus. Okay, therefore it's a descending sequence, right? Therefore, what do you get? You get this implies by the continuity of measure limit n tending to infinity of measure of En is equal to measure of this. Because you get the intersection of Ens. Okay. And you have this is a descending sequence, therefore you have this is equal to this measure of the empty set, which is in turn equal to 0. So we have this result. So this is what you have. So measure of En goes to 0, infinity. This is of course a descending sequence. It's a descending sequence. Okay. Now choose a natural number. Okay. Now choose natural number. N such that measure of En naught now you choose a partition of N naught. What you are doing is this is 0, this is minus n, this is plus n. We are taking this one and intersecting with the E. That is how we are constructing it for each n. Okay. So you take a partition of minus n naught to n naught. And express E intersection sorry. Sorry, it is not E. No? as a disjoint collection of sets measurable subsets each of length each of which has measure less than. Now that is possible because what you are doing is you are taking this interval minus n naught to n naught and then divide this, okay, such that the length of the interval is less than delta. So the number of divisions will come there, okay, and then you see that however it is finitely many. Take the intersection of each of this with E, so you get the union of this, and the part of E over here outside this is of measure less than delta. So that is taken as one block as we did in the previous case, okay. Then we have the following, that is, what is it? E equal to E n naught union an, where an is equal to ai equal to E intersection minus I to I. This is measurable. Okay. Now clearly you see that ai intersection aj is okay, ai such that this one, that is not minus I to is into subintervals. ai into, so you can write this as a union of intervals. So you write this one such that ai bi intersection aj j is n. That can be done whenever I is not equal to, okay, that is your ai, and then clearly see that, and also such that bi minus ai is less than delta. Okay. So you have measure of, and whatever you have left out here, measure of okay. So that is the strategy. Thus each of this one, that is measure of That's how you do. Therefore, you can always do this. Given delta, you can always find a partition of the measurable subset E with finite measure into a disjoint union of measurable subsets. The length of each of this subset is less than delta. So that's something that we are going to work on. Okay, right. So this lemma is very useful in proving our next theorem. So I think it's fairly long now. I think I will wind up here and then continue with the main theorem in my next lecture. I have already talked about the preliminaries of that, but I will do that next time. Thank you very much. So what is important is that one should not miss the art of analyzing it, comparing it with the case of money that we are familiar, and then what to expect, and then from that we start statement of the theorem, and then try to, or how to generalize the situation from Riemann integral to Lebesgue. Okay, thank you very much.